Greetings to all of you. I'm going to explain rotational spectroscopy or microwave spectroscopy in this video lecture. In order to explain the rotational or microwave spectroscopy, we have to go for the selection rules. What are the selection rules? Right? So, an absorption of electromagnetic radiation, this is called as coupling mechanism. So, an electromagnetic wave is a oscillating electric field and it interacts only with molecules that can undergo change in dipole moment. So, for a molecule to be microwave or to exhibit rotational spectra is it should have change in dipole moment. So, the oscillating dipole can be provided by the rotation of the permanent dipole like you take example of HCl. So, this type of interaction leads to the microwave spectra. So, in case of HCl, see here H positive charge, chlorine negative charge. When there is difference in their electronegativities, obviously when you are going to rotate the molecule, the direction of rotation is going to be changed. With respect to the direction of rotation, direction of dipole also will changes. See. So this is, imagine HCl minus. We have turned 60 degrees, again 90 degrees, again 90. Yes. So like this, if you rotate either 60 or 90, something like that, we are going to observe the change in direction. With respect to this change in direction, we are going to observe the direction of a dipole. So, this is the plot, vertical component of your dipole, like this. This is the plot, right? So, the rotation of a polar diatomic molecule showing fluctuation in the dipole moment measured in a particular direction. Yes. So here we are going to explain about the rigid rotor. This is rigid rotor. A diatomic molecule may be thought of as two atoms held together with a massless rigid rod or simply called as rigid rotator model. Right? So consider a diatomic molecule with different atoms of masses M1 and M2. For example, you can take HCl only, hydrogen consider the mass M1 and fluorine consider the mass M2. Like this, whose distance from center of mass are R1 and R2 respectively. Right? So the moment of inertia of system about the center of mass is I is equal to M1 R1 square plus M2 R2 square. I is nothing but called as a moment of inertia. Right. So according to Schrödinger equation, we are going to measure about this quantization of energy or quantization of rotational energy. So which is given by h square by 8 pi square m into dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus v of these x, y, z are called as Cartesian coordinates and psi, the wave function, is equal to E of psi. If v is equal to 0, it means the cyclic boundary condition psi of 2 pi plus theta is equal to psi of theta. So by solving Schrodinger equation for rotation molecule, the rotational energy levels, after you solve all these things by taking starting from Schrodinger, if you have interest, you please try on a separate paper, and finally you are going to get epsilon of j is equal to h square into j of j plus 1 by 8 pi square I. What j stands for? So this rotational spectra is nothing but we are going to deal about rotational energy levels. Moreover, these rotational energy levels are called as rotational quantum numbers. So being quantum numbers, they will be given numbering as 0, 1, 2, 3, etc. So rotational energy levels this is in case of energy. Let us suppose say joules. Now we have to convert in terms of wave number. The units are centimeter units. So this epsilon j divided by hc, which gives a wave number. Right? So for this whole divided by hc, finally after simplification, we are going to get h by 8 pi square c into I into j of j plus 1. So if you look at this, there are many constants. H is Planck's constant, 8 itself is constant, phi value is also constant, c is constant, and I moment of inertia for a particular molecule is also constant. So in order to replace all these constants with a letter, let us imagine it is B. So hence this can be rewritten in the form of B of j into j plus 1. So in case of rigid rotor, we are going to take about the moment of inertia about c. So as I said you, I is equal to m1 r1 square plus m2 r2 square in the previous section, right? So if r1 is equal to r2 or m1 r1 is equal to m2 r2, overall we are getting m1 plus m2 into r1 r2, where I is moment of inertia. After simplification, overall we are going to get m1 m2 by m1 plus m2 into r0 square. This m1 m2 by m1 plus m2 can be rewritten in the form of mu r0 square. What is this mu stands for? Mu stands for reduced mass. Okay? So a diatomic molecule can rotate around a vertical axis. The rotational energy is quantized. So by using Schrodinger equation, the rotational energy levels allowed to the rigid diatomic molecule are given by, so just now only I said epsilon j is equal to h square by 8 pi square j into j of j plus 1. This is in terms of joules. I have explained in terms of wave number also. So j is rotational quantum number. J is equal to 0, 1, 2, 3, etc. I is moment of inertia. mr square. U is reduced mass. m1 m2 by m1 plus m2. And r is internuclear distance. So this is how we are supposed to define the terms. And in terms of wave number, the units are centimeter inverse, and it's given B of j into j plus 1 centimeter inverse. Now we are going to explain about the rotational spectra of a rigid diatomic molecule. So the rotational energy levels for rigid rotor. Finally, what you have written? So this one already I have explained. J is rotation quantum number. Our rotational energy is 0, 1, 2, 3. Like this is all constant. Finally, we got epsilon j is equal to B of j into j plus 1 centimeter inverse. So j is equal to this one. Now we have to substitute those values in this one. epsilon 0 is means that ground state, one is first level, first energy state, second 2 is second energy level, like this, right? So where B is the rotational constant, which can be given by h by 8 pi square. I say overall this is replaced by B, right? So centimeter inverse means we are calculating this energy in terms of wave number, and I is reduced mass, as I said to m1 m2 by m1 plus m2 into r0 square, which can be written as mu r square. So this is the representation of a rotation of a rigid diatomic molecule, right? So for rigid rotor, suppose say from which level to which level it is going to go? From J to J plus 1. So mu of J to J plus 1, it is equal to 2B into J plus 1 centimeter inverse, correct? So you have to calculate J is equal to 0, 1, 2, 3, 4, like that, so on. You please calculate. Finally, in a generalized statement, you can write this. So for this, if you write for epsilon of 0 is equal to J of J plus 1, overall you are getting 0 only. Then J is equal to 1. If you substitute all those values, you will be getting 2B. J is equal to J is equal to 2, second energy state. You are getting 6B, 3, 12B, 4, 20B, 5, 30B, like this we are going to get. So the same thing here from 0 to 1, 1 to 2, 2 to 3, like this, the energy changes will be taken. What is epsilon delta J is equal to, it means plus or minus 1, the difference between any two successive energy levels. Let us suppose say take from 3 to 4. 3 it is 12B, 4 it is 20B, 20B minus 12B, 8B, here we got 8B. So like this, 5 to 6, 30 minus 42, 12B, like this. So overall if you see 2B, 4B, 6B, so any difference we are going to get only 2B. So though here it seemed to be, as the size is going to be increased from one level to, as we are going to the next higher energy levels, but here in this scenario we are going to observe that the lines are equally spaced. So this is nothing but which is called as the allowed transitions between the energy levels of a rigid diatomic molecule and the spectrum. This is, once again I repeat, these are the allowed transitions in which we are going to consider delta J is equal to plus or minus 1 between the energy levels of a rigid diatomic molecule. So this is very important derivation in the examination point of view. So in the next class, I will tell you the remaining part of the microwave, that is the rotational spectroscopy. Thank you.